Welcome to the geologic cross-section of southeastern New York laboratory for the Geology 2 class. What we are going to be doing in this presentation today is taking a tour of the bedrock geology of primarily eastern New York and the Hudson Valley. And we are going to collect some data and make some observations and interpretations that we will use to construct a geologic cross-section, and from that geologic cross-section we will interpret the geologic history as revealed by the rocks of New York State. Let's begin on Long Island. And Long Island is a relatively recent addition to geologic history, having been formed from the melting of the continental ice sheet associated with the last major ice age, the Wisconsin glaciation. So the ice came down from northern Canada and spread south and finally reached a point at the position of Long Island where the flowing of the ice was matched by the melting of the ice. And so the position of the ice stabilized, and as it flowed and melted and flowed and melted, it deposited a large pile of mostly sand and gravel, which makes up Long Island. And the position of the ice is marked by these ridges of hills, which are called moraines, that run west to east across Long Island. There's a line of hills to the north called the Harbor Hill Moraine and the Ronkonkoma Point Moraine. The Ronkonkoma Point Moraine forms the north fork of Long Island, and then kind of branching off in the western Long Island is the Ronkonkoma Moraine, which extends eastward to form the south fork. So the geology of Long Island is glacial geology. Again, mostly unconsolidated sands and gravels. And if we go to Google Earth, so let's start our tour by heading down to Long Island, kind of like coming in like we're landing from outer space. All right. So we're going to start from the Hofstra campus, and there are many places on Long Island to observe the glacial geology. Most of them are on the coastline, either along the North Shore or out at Montauk Point. Other places to see glacial geology in New York State are valleys in upstate New York. And, well, really pretty much anywhere you go in New York State, you see evidence of the last ice age, because glacial ice covered every single inch of New York State up until about 20,000 years ago when the ice began to retreat. Today, we're just going to make a short stop, not too far from Hofstra, so we're going to head west to Baisley Pond Park. And there really isn't too much geology to see at Baisley Pond Park, but there's some interesting history at Baisley Pond Park. And the indication of that history can be found on the playground. If we zoom in here, there's a sculpture that you can see in the Google Earth image here on the playground. We can pull up a photo of it in Google Earth. So back in 1855, some workmen were enlarging the pond because it was going to be part of a water supply system for Brooklyn, and they uncovered the bones and teeth of part of a skeleton of a mastodon. And so a mastodon is a extinct furry elephant that used to be widespread across North America. And the remains of mastodons, like this tooth you see in the lower right here, are fairly common fossils in New York State. Every 10 or 20 years, somebody finds a mastodon skeleton at the bottom of a pond somewhere in New York. In the upper video, you can see an example of the kind of deposits that were left behind by the glaciers, pebbles and cobbles and sand. And you can find, as I said, glacial deposits pretty much everywhere across New York State, particularly in the valleys. On Long Island, all of Long Island is glacial. All right, so from Baisley Pond, we are going to head west again over to Manhattan. So when we cross over to Manhattan, we leave the glacial deposits of Long Island, and in Manhattan we see lots of exposed bedrock. There are glacial deposits in Manhattan as well, but in Central Park you can see exposures of bedrocks. Southern Central Park's a particularly good place. There's a large exposure called Umpire Rock, which is a good place to take a look at the geology. So let's go back to the PowerPoint. And so this is a photo of a typical exposure of bedrock in Central Park. And so you get a look at the underlying geology, but you can also see evidence of the last ice age. So we have some of the oldest rock, not the oldest rock, but some of the oldest rock in New York State in the bedrock, but we also have evidence of some of the youngest geological activity, the advance of glacial ice. So in the photo here, you see this large boulder. This is a glacial erratic. It's a chunk of rock picked up by the ice and carried along and kind of tumbled and rounded, and then when the ice melted, it was just left sitting behind on the bedrock surface. And then the bedrock surface itself, you can see, is very smooth and kind of rounded. It's been carved and polished by the flow of ice, and there are large grooves and small striations carved into the bedrock surface. The bedrock itself that you see in Central Park is a formation called the Manhattan Schist. And you can see in the video here that it's a very pretty rock. It has large flakes of glittery mica that shine in the sunlight. And so if you hike around the rock outcrops in Central Park on a sunny day, you see all these glittery mica crystals. And also embedded reddish crystals of garnet. You can see that in the photo, in the video as well. The Manhattan Schist is a high-grade metamorphic rock, meaning that it formed under the roots of an ancient mountain range, and we can date the rock, and dating the rock gives us the age that it was turned into metamorphic rock when the rock was heated up, which kind of resets the clock, and we get a uranium-lead age of about 450 million years for the Manhattan Schist. And the geological region that we're in is the Manhattan Prong. We'll take a look at that in a second here. So we go back to Google Earth. Let's just get a little bit of an overview. So we're going to fly up and get a bird's eye view. And then we take a look at the map of physiographic provinces. We see that Long Island is part of the Atlantic coastal plain. It's a pile of sand and gravel sitting on top of the coastal plain, which is really just the continental shelf that then extends up onto the land in eastern New Jersey and southward. Leaving Long Island, we leave the Atlantic coastal plain and we come down in a region called the Manhattan Prong, which extends up through Manhattan, the Bronx, and into Westchester and Connecticut, and up even into Massachusetts. On the other side of the Hudson River, as we'll visit that in a little while, we have a region called the Newark Lowlands, and we'll talk about that. And then when you continue north and west, you leave the Manhattan Prong and you enter a region called the Hudson Highlands. So from Central Park, let's travel a little bit further north, up the spine of Manhattan. So again, Google Earth is kind of bringing us down like we're landing in a rocket ship. And we come down just north of Manhattan in the Bronx, and we are positioned over the Cross Bronx Expressway, which is the highway you take to get to the George Washington Bridge to head over to New Jersey. And I chose this particular view because you can see in the center the highway goes under a little tunnel, and the tunnel is blasted out of the bedrock in this region of the Bronx, which is called Fordham. And the bedrock that's exposed is a rock formation called the Fordham gneiss. The Fordham gneiss is a very stripy looking high-grade metamorphic rock, and in some ways it's similar to the Manhattan schist. It does have some layers of mica, but it's much older than the Manhattan schist. The Fordham gneiss is an example of the basement rock under eastern North America. This is the rock that forms the foundation of the eastern part of the continent. It's called Grenville. We talk about this large region of metamorphic rock under eastern North America. We call it the Grenville terrain. And it's deeply buried in most places, but it pops up to the surface for various reasons here and there. And Manhattan and Westchester is one area where this older rock is exposed at the surface. How old is the rock? Uranium lead dating tells us that it dates back to about 1.2 billion years. So this is from the late Proterozoic. And again, it's a high-grade metamorphic rock. So that tells you that it was once part of the roots of an ancient mountain range. An older mountain range than the mountain range that formed the Manhattan schist, because the Manhattan schist is half as old as the Fordham gneiss. So just looking at the metamorphic rock in New York City, we see an older layer and some younger layers. So we just take a look at a cross section, which kind of parallels the Cross Bronx Expressway, going from kind of north of Long Island in the Bronx across to the Harlem River, upper part of Manhattan Island, and then to the Hudson River here, right? And you can see there's the Fordham region up top. So the rock that's underneath the Manhattan Prong in the New York City area, the deepest rock is the Fordham gneiss. That's shown in the brown, but there are places where, because the rock is folded up and down, there are places where the deeper rock comes up to the surface, and we can see it. And then sitting on top of the Fordham gneiss is the Manhattan schist, and between the two is a formation called the Inwood Formation. The diagram says limestone, but it's really a marble. It's a high-grade metamorphic rock. It started out as a limestone, but it was turned into a marble. So the Inwood marble has the same age of metamorphism as the Manhattan schist. So we're looking at metamorphic rock that's showing us the roots of two ancient mountain ranges separated from each other by about 500 million years. Okay, so from Fordham, we are just going to travel a little bit further north. And we're going to come down in Westchester, pretty close to the Tappan Zee Bridge. And I just wanted to show in Google Earth, there are some relatively fresh road cuts in the highway that takes you to the Tappan Zee Bridge. And in these road cuts, you can see examples of the Fordham gneiss, this very, very stripy looking metamorphic rock. All right, now I'm going to cross over the Hudson River. So there's the Tappan Zee Bridge, crossing over the Hudson. We cross over a little region that sticks up out of New Jersey, which we'll come back to. We go up into the Hudson Highlands, and there's Bear Mountain, which is one of the very accessible points in the Hudson Highlands. You can drive to the top of Bear Mountain, park your car, and hike out to the kind of the edge of the cliffs there and have a good look around and get a good look at the bedrock underneath your feet. What kind of bedrock do we have in the Hudson Highlands? Well, we have very crystalline, almost igneous-looking rock, large crystals of feldspar and quartz, the same mineral composition that a granite has. So very much this rock appears to be a granite, except if you look carefully, what you notice is that the crystals seem to have an orientation. There are stripes or bands of mineral crystals. You see that sort of dark stripes cutting across the rock from left to right. That tells you that this rock has been put under tremendous pressure and that it's a metamorphic rock. So we call it a metagranite. It has the appearance and the minerals of a granite, and it was almost certainly a granite at one point, but then it got caught up in a plate tectonic collision and metamorphosed into a metagranite. Another name for metagranite is a granite gneiss, because it's mineralogically, it's a granite, but it has the texture of a gneiss, a metamorphic rock. The uranium-lead age for the rock in the Hudson Highlands, including the Bear Mountain granite, metagranite, is the same age as the Fordham gneiss. So we're talking about, again, the basement rock underneath eastern North America from the late Proterozoic. And if you travel around the Hudson Highlands, you see examples of metagranite, you see examples of other types of meta-igneous rock like metadiorite, and you see lots and lots of high-grade metamorphic rock like the Fordham gneiss. So we have a very broad terrain with different types of high-grade metamorphic rock, and the overall impression we get is that we are looking at rock that got caught up in an ancient plate tectonic collision and buried under a very large mountain range. All right, from the Hudson Highlands, we are going to travel to, we're going to backtrack a little bit. We are going to go back down to the Hudson, and we're going to take a quick look at what's lying across the Hudson River from Manhattan Island, and that's the Palisades Cliffs. If you've ever crossed the George Washington Bridge on a nice day, certainly you would have noticed this beautiful, very, very steep cliff line that stretches northward along the Hudson River. And if you follow the Palisades Cliffs, they take you pretty much up to the gateway to the Hudson Highlands. And if we just sort of fly upward here a little bit, so the Palisades Cliffs start out across from lower Manhattan, and they run up the west side of the Hudson River. And then the cliffs kind of wrap around and then sort of disappear as they butt up against the border of the Hudson Highlands. And the curvature of the Palisades defines this very, very large region that is mostly in New Jersey but crosses the border into New York State. And this is the Newark Basin, or the Newark Valley lowlands. And what's interesting about the Palisades cliffs is that they are made out of a particular type of igneous rock that is very much related to the kind of rock that forms the ocean floor, the kind of rock that erupts at mid-ocean ridges, or over hot spots to form oceanic islands like Hawaii. So it's very different from granite. The rock in the Palisades cliffs is called diabase, and it's very similar to basalt. It's basically a coarse-grained version of basalt. There are other examples of this kind of rock in New Jersey. So if we fly westward across New Jersey a little bit, we come to the town of Paterson. And in Paterson, New Jersey, there's a very impressive waterfall called the Great Falls, where the Passaic River flows over the face of a cliff that's kind of similar to the Palisades. So you have this very steep drop in the landscape caused by a thick, very erosion-resistant layer of igneous rock. But in Paterson, this is not diabase, this is basalt. It's called the Orange Mountain basalt, and it's about an 80-foot thick layer. And the Passaic River has eroded a small gorge along a fault line, and where the water tumbles into the gorge, you have these beautiful waterfalls. So if we zoom back out again, we have a lot of geology in this region, in the Newark lowlands. If I bring up the physiographic map again, you can see the Newark lowlands extend, as I said, up through New Jersey and over the border into New York State here. A better view can be revealed if we put up a geologic map of New Jersey. Give it a second to load. Come on. No, there we go. So it's this very, very broad region here, and the pink rock along the eastern margin is the diabase of the Palisades. Of course, the geologic map ends at the border. Each state makes their own geologic maps, so we can add in the New York part here. Bear with me a second while there we go. So now you get a kind of sense of the whole region here. There's the sort of hot pink rock representing the Palisades diabase. It wraps around, and then it stops where the Newark Basin lowlands give way to the rock of the Hudson Highlands, this green rock. And the geology of the Hudson Highlands is very complicated. Lots of different rock formations because, again, you're looking at the metamorphic roots of an ancient mountain range, and you have lots of different types of rock that have all been kind of smushed together. So in the Newark Basin lowlands, we have, besides the Palisades, we have layers of basalt, which are basically lava flows that are exposed at the surface in the central part of the Newark Basin. Now, So there's a view of the Palisades cliffs. The sheet of igneous rock is referred to as a sill. There's a photo of the Great Falls at Patterson where the falls cross or fall down over the cliff formed by the Orange Mountain basalt. There's one more place you can see similar types of rock, and that's actually up north of the Hudson Highlands, just along the border of the Hudson Highlands. There are a few places where there are thin vertical walls of basalt. They're called dikes, basically faults along which the magma was able to work its way up towards the surface. So the same kind of magma that was erupting to form the lava flows in the Newark Basin lowlands, and that was injected between already existing layers of rock to form the Palisades sill. Some of those magmas reached the surface a little bit further north and cut their way up along the older rock strata. The age of all of this igneous rock is about 200 million years old, which is the beginning of the early Jurassic. So these eruptions happened relatively recently, kind of, the beginning of the age of dinosaurs. And before we move on, it's worth taking a look at a cross-section across the Newark Valley, what's called the Newark Rift Basin. So there's New York City and the Hudson River to the right. You cross over the George Washington Bridge and you see the cliff face formed by the Palisades diabase, which is this sheet of rock, of igneous rock that comes up to the surface, and it parallels the underlying and overlying sedimentary rock. So the whole region has been tilted to the west, and as you drive along Interstate 80 towards Patterson, you're driving across layers of sedimentary rock deposited during the Triassic, and then when you get to the region of Patterson, you encounter the first of 3 lava flows that form these ridges, and then the rock, as you travel west, you're traveling up the pile of rock, and the rock gets younger, and you work your way into the very, very lower part of the Jurassic. And on the other side of the Newark Basin is a very large fault called the Ramapo Fault, and that's the fault along which the crust dropped to form this ancient rift valley. So what you're looking at across the Newark Basin is what was an active rift valley, like the rift valleys in East Africa, that was forming 200 million years ago or so. Okay. Let's turn off the geologic maps because we don't need them anymore. All right, so from the Newark Basin, we are going to fly north. So you can see the tip of the Newark Basin, the mountains of the Hudson Highlands, and we come down along the New York State Thruway, not far from Harriman, and it's in the rocks exposed along the highway that, driving by at 60 miles an hour, you can see some of these thin black vertical layers of igneous rock that are cutting up across the sedimentary rock. Unfortunately, I don't have a good photo to show you because you're not allowed to stop along the thruway, and it's hard to take a decent picture driving past. So you just have to imagine it. All right. So from here, we are going to head north up the east side of the Hudson River. Or, I'm sorry, the west side of the Hudson River. We'll come back down the east side of the Hudson River. So I'm going to zoom out here a little bit so we can see all of the places that we're going to visit. Whoops. And let me put the physiographic region map back on. So we started in the Atlantic coastal plain. We traveled up the Manhattan Prong. We paid a visit to the Newark lowlands. We stopped in the Hudson Highlands. And now we are going to continue north through the Hudson Valley, what's called the Hudson Mohawk lowlands. And we are going to be visiting some locations which are along the edge of the Catskill region. And then we'll head up into the Allegheny Plateau, come back to the Newark Basin lowlands, and then head way up into the Champlain lowlands along the edge of the Adirondack Mountains. We'll come back down through the Taconic mountain region back into southeastern New York to finish our tour. If we take a look at the geology, we can throw up some geologic maps here. So the geology of southeastern New York is very complicated. But once you start to head north and west, it gets a little bit less complicated. You see broader regions of rock. The Allegheny Plateau is this very, very large region in shades of green here. The green represents the colors represent the age of the rocks, not the rock types. And green shades on this map are generally rock that formed during the Devonian period. So you see there's a lot of Devonian age rock in New York State. The pink rock is Silurian aged rock, as is the purple down here. And then the orange and beige and red is Ordovician in age. So we have a pretty good sequence of rock from the lower and middle Paleozoic, which we're going to be looking at here. All right, so let's go to our next destination. We're going to fly down to New Paltz. So we're crossing the Wallkill Valley from the Hudson Highlands, and we come to the base of this long ridge called the Shawangunk Ridge, and you can see that the rock that forms this very, very steep ridge is very light in color, but down below, just by where the road curves around in this hairpin turn, you see some much darker looking rock, and that's the rock that we're going to look at right now. It's sedimentary rock that is underneath the valley, and then it comes up and it's sitting underneath this lighter colored rock that forms the ridge here. The rock of the valley is called the Normanskill Shale Formation, and then the rock of the ridge is the Shawangunk conglomerate. So the Normanskill rock is a dark gray to black shale, splits into nice flat pieces. You can find fossils if you look very carefully, and the most common fossils are graptolites. You can see them on the split surfaces of the shale. Graptolites were a planktonic colonial organism that was floating around in the oceans that covered New York State back in the Paleozoic, and then when they died, they would sink down to the bottom into the mud. There's a particular species in the Normanskill called Climacograptus, which is a species that's used to identify the middle Ordovician. So we can date the Wallkill Valley shales, the Normanskill Formation, using the graptolite species. And this rock represents a deep water environment, kind of a deep basin that formed across eastern North America and flooded with marine waters back in the middle Ordovician. Another thing to note about the Normanskill Shale is that pretty much wherever you see it, you don't usually see it lying horizontal. You see it vertical, as it is in the photo in the lower left, or you see it at an angle, or you can see folds in it. So this rock, after it was deposited, was shoved and pushed up by some kind of tectonic event. And in the photo in the lower left, you can see me in the center of the photo, and I'm pointing to the boundary between the blocky late Silurian age rock, which is limestone, that is sitting on top of the Middle Ordovician Normanskill Formation. And you can see that the Normanskill layering comes up and intersects the late Silurian rock at an angle. So this is a good example of an angular unconformity. And if you think like a geologist, you think that, okay, originally those Middle Ordovician layers were deposited flat. They were deposited horizontal. And then something came along and pushed them up, and then they eroded down to a flat surface. And on top of that flat surface, the late Silurian rocks were deposited. But those rocks are tilted, which means the whole pile, at some point after the late Silurian was deposited, the whole pile was pushed up and tilted again. So in this photograph here, you see evidence for two distinct episodes of uplift, which means two distinct episodes of tectonic collision and mountain building. The first episode tilts the Middle Ordovician rocks, so it must have happened after the Middle Ordovician, but before the late Silurian, because by the late Silurian, those rocks had been eroded flat, and the late Silurian rocks were deposited horizontally. And then sometime after the late Silurian, the whole pile of rock was tilted again to bring them into their present position. So from the base of the Shawangunk Mountains, let's travel up to the top of the Shawangunks. And in the region of New Paltz, instead of having a single ridge, you actually have a double ridge. So these layers have been folded into kind of a double wrinkle. And a really good place to see the Shawangunk conglomerate is Minnewaska State Park. If you drive or hike to the top, there's a beautiful lake you can picnic along, and you see this beautiful white rock off in the distance on the other side of the lake. And of course, you see it everywhere you're hiking around on it when you're up at Minnewaska State Park. So this is the Shawangunk conglomerate. It's a very pure quartz pebble conglomerate. Very, very hard and erosion resistant. In the photo in the lower left, you can see these beautiful white layers of Shawangunk conglomerate. It's 99.9% pure quartz. Now, the environment of deposition for the Shawangunk conglomerate is interpreted to be a large coastal river system that was draining off of a well-eroded highland somewhere off to the east. And about the only minerals that survived by the time the river reached the New York area was the very erosion-resistant, very hard quartz pebbles to deposit to form the conglomerate. There are no fossils in the Shawangunk conglomerate, no evidence of any marine influence. But if you follow the Shawangunk conglomerate south, that ridge crosses into New Jersey, where it's called Kittatinny Mountain, and you can follow the same layer of conglomerate all the way down through Pennsylvania into Maryland, Virginia, and North Carolina. By the time you get down into Pennsylvania, you start to find evidence of the environment of deposition changing from a river environment to a shoreline environment. The Shawangunk, well, it changes its name. It becomes the Tuscarora Formation, and it becomes more sandy and less pebbly, just a very thin interval of conglomerate in the Tuscarora. And you do find some marine fossils when you get down into Pennsylvania, including this very interesting trace fossil in the video on the bottom right. These are burrows in sand made by some multi-legged animal, possibly a trilobite. And as it was crawling through and digging its burrows, it left behind these it's a two-lobed burrow with these parallel scratch marks made by two sets of legs on either side of the animal digging away. Okay, now from Lake Minnewaska, we're going to travel north a little bit So start with an overview here. So there's Lake Minnewaska, the two localities we just visited, and now we're going to head north up into the high peaks of the Catskills. We're going to follow a highway that starts out in the vicinity of Leeds, New York, and takes you through Catskill, the town of Catskill, and then up into the high peaks region of the Catskills. So we'll fly down, take a look. Now, the Catskill Mountains are carved into a pretty much flat line layer cake of sedimentary rock that's been very, very gently uplifted to produce the mountains. You get a hint in the photo in Google Earth of the horizontal layering of the strata. And driving the highway up into the Catskills, just highlight the highway there. That's New York Route 23A. All along this highway, you can see beautiful road cuts exposing the underlying rock. Here's a photograph in the lower left that shows what that rock looks like, particularly when you get up high into the Catskills. You see big, thick layers of sandstone, kind of light gray to beige in color, and then these very, very reddish layers of siltstone, sandstone, and shale. These rocks represent river channel and floodplain environments. So you have sandstones and conglomerates in the river channels, and then the floodplain deposits consists of thin layers of sand and then lots of mudstone and shale. All of it colored deep red from the oxidation of iron. So these are red beds. So we're looking at environments that existed above sea level, exposed to oxygen. And then the fossils that you find in these rocks, you can find plant fossils, the remains of some of the world's oldest trees and forests. And the example that is in the video is a plant called Archaeopteris, which is the oldest seed-producing tree that's ever been found. The slab of rock I'm holding in the video shows a piece of a branch with, you can see the sort of the sticks, and then just some very faint impressions of these very small leaves that grew off of the branches. All right, from here we are going to fly north, kind of along the margin of the Catskills, and we're going to come down not far from Albany, along another cliff. Cliffs are very good places to see examples of the underlying geology. All right, so let me just go back to the bird's eye view here for a second. It's a little bit confusing sometimes the way Google Earth sort of spins you around. So I think it's good to kind of orient ourselves. So we went from Lake Minnewaska up to the high peaks region, and now we're going to continue north. We're going to leave the high peaks, and we're going to come just kind of to the edge of the Allegheny Plateau. If I turn the physiographic map on here, so this the Catskill Mountains region, we're going to be just on the edge of that, where it borders the Hudson Mohawk lowlands, and then from there we are going to travel west into the region of the Allegheny Plateau before we go back to the Newark Basin lowlands here. So let's fly back down to the, bear with me a second while okay, so we're going to go back to a place called John Boyd Thatcher State Park, one of the least well-known and most beautiful state parks in New York State. The park is situated at the top of a very, very long cliff line where the level of the landscape drops down, and in the base of the cliffs you see the Normanskill Formation. You see those same black shales that are underneath the Shawangunk Formation further south. But up a little bit further north, near Albany, you don't have the Shawangunk rock anymore. It wasn't deposited this far north, and instead what you see are is a big thick pile of limestone from the lower Devonian, exposed in the cliffs along John Boyd Thatcher State Park. These limestones contain lots of fossils, so it's easy to date them. The fossils tell us that the limestones are from the lower Devonian, and the type of limestone and combined with the fossils tell us that these were shallow water coral reef-like environments. And in fact, fossil corals like the Favosites coral head in the lower right of the lower right video are very common in these limestones. So we have brachiopods and we have corals. Now we're going to head west from John Boyd Thatcher State Park out into the Allegheny Plateau. So we're looking to the south here. You see some Finger Lakes off in the distance, some of the eastern Finger Lakes. And there's a little town called Hamilton. So this is a sort of a region of rolling hills. Not really mountains, just hills. It's very rural, lots of farms. And every now and then along the rural roads you see some outcrops of shale poking out from the subsurface. And if you poke around in the shale, you can also find fossils, but these rocks are not limestones. They're mostly shale with some greywacke and a little bit of sandstone. It's a big, thick sequence that underlies much of the Allegheny Plateau. These rocks represent deep to shallow water environments where lots of sediment was being washed in to produce these detrital sedimentary rocks, the shale, the greywacke, and the sandstone. You find fossils of corals and trilobites and brachiopods. There's a trilobite called Phacops. That's kind of the body and the tail. The head is missing off that piece, but there's a head. He's got these kind of bug-like compound eyes on either side of the center of the head there. So these are fossil species characteristic of the Middle Devonian period. So now we've kind of looked at some examples of rocks from the early Devonian to the middle Devonian to the late Devonian, and let's just think about that for a second here. If we go back to the bird's eye view, so we kind of jumped around, but at John Boyd Thatcher we see the bottom of the Devonian. At Hamilton, we see the middle of the Devonian. At Catskill, we see the upper part of the Devonian. And let's put a geologic map down so we can see what this looks like. Okay. So the green shades represent the Devonian, and the oldest layers are exposed along the edge of the Allegheny Plateau at John Boyd Thatcher. That's lower Devonian. And then the kind of lime green, well, actually, I don't know what kind of light green here is the middle Devonian, and there's Hamilton up in the middle Devonian. And then the stippled kind of yellow-green is the upper Devonian, and there's Catskill Falls in the upper Devonian. We can take a look at that. Can pull up a map key here, and we can see this represented a little bit better. So there's the geologic time scale of the Devonian, the early Devonian, the middle, and the late Devonian. So the brighter green is the early Devonian rocks. Formations like the Rondout limestone and the Manlius limestone and the Queemans limestone, those are the formations you see at John Boyd Thatcher. And then you get up into what's called the Hamilton group in the middle Devonian. That's what you see at Hamilton. And then up in the Catskills, you get up into the later part or the upper part of the Devonian into the Shawangunk group, Slide Mountain. There's a whole bunch of different named rock formations. And the overall trend is the lower Devonian rocks were deposited in shallow water. They're limestones primarily, and then the middle Devonian rocks are shales deposited in deeper water, and the upper Devonian rocks are shales and sandstones and conglomerates deposited in shallow water and in many cases above sea level in river environments. Okay. From Hamilton, we are going to leave the Allegheny Plateau and head north to Saratoga Springs, north of Albany. And let's take a look at the rocks that are exposed in the lowlands surrounding Albany. We have limestones of the Hoyt Formation, and these are older limestones. They're not lower Devonian; they're late Cambrian. So we're going back in time to the beginning of the Phanerozoic eon, to the beginning of the Paleozoic era in the late Cambrian. And these are near-shore deposits, shallow marine waters, and you find fossils in the Hoyt limestone. You can see some snail or gastropod fossils in this piece of limestone. The most impressive fossils in the Hoyt limestone are bacterial mud mounds or stromatolites, which are beautifully exposed in some places. There used to be a roadside attraction called Petrified Sea Gardens, where you could pay a couple dollars and then hike around and see these beautiful cabbage head-like stromatolites exposed in the weathering limestone outcrops. In the video, you're looking at a chunk of stromatolite that's been cut with a saw, so you can see the internal layering produced by the growth of the bacterial mats trapping the mud to form the stromatolite. So we have limestones in the Saratoga Springs area that are a lot older than the limestones that we saw before. So again, let's kind of get the bird's eye view here. So there's the Adirondack Mountains. And we'll just slide down a little bit. If we pull up the geologic maps again, so Devonian rocks in the Allegheny Plateau, and now we've come north of the Allegheny Plateau across Ordovician age rocks, and we get down into the blue here. These are Cambrian age rocks. So as you travel towards the Adirondacks, you're moving down through geologic history. You're moving into older and older rocks, and the rocks that surround the Adirondack Mountains date back to the beginning of the Paleozoic. So we have Cambrian limestones, and then we're going to take a trip way up along the edge of the Adirondacks to a place called Ausable Chasm, where the Ausable River has carved a gorge that exposes some of the oldest sedimentary rock in New York State. So let's head up to the Ausable River. Not far from Lake Champlain along the New York-Vermont border. View of the high peaks of the Adirondacks. And there's the Ausable River and the gorge that it's carved in the underlying rocks. And the rock formations that are exposed along that gorge are sandstones of the Potsdam Formation. So these are very clean quartz sandstones, layer after layer of quartz sand, deposited in a shoreline environment, a beach environment, really. In the video here, you can see the sand grains that are cemented together to form the sandstone. There are some amazing fossils in the Potsdam Formation, including a trace fossil, which is a trackway made by a very large multi-legged animal. You can see that whatever made these tracks was crawling along, leaving these furrows as its legs moved back and forth from side to side. And the width of the animal was almost a foot. So we have no idea really what the animal was, except that it had lots of legs. So some kind of giant millipede or a very large trilobite. We don't know, but it's interesting to contemplate. And there are places where the surface of the sandstone is just crisscrossed with hundreds and hundreds of these tracks. So whatever animal this was, it was pretty common, way back in the Middle Cambrian. And as I mentioned before, the Potsdam Formation is pretty much the oldest sedimentary rock that you can find in New York State. It sits beneath the Hoyt limestone. So you have a beach environment that existed first, and then you transition from a beach environment to a shallow water marine environment where you form limestone. Okay, now from the Ausable River, we are going to head back down south, but we're going to head down south along the east side of the Hudson River. And we're going to pause to get a bird's eye view of a low mountain range that skirts the border of New York State, the border of New York State and Connecticut up into Massachusetts, and we call these the Taconic Mountains. The Taconic Mountains are mountains that are made up of metamorphic rocks, so they're sort of similar to the Hudson Highlands in that respect. They're formed from metamorphic rock, but it's a very different kind of metamorphic rock. The rock in the Taconic Mountains is very similar to the sedimentary rock that you see in the Hudson Valley, except that it has been very modestly converted into metamorphic rock, meaning that the rock was probably not buried under an ancient mountain range. We're not looking at the roots of an ancient mountain range. What we're looking at is rock that was buried under some amount of overlying rock and put under tremendous pressure. And the interesting thing about the Taconic region is that you can, if you map the rocks in the Taconic Mountains very carefully, what you can demonstrate is that all of this rock has been shoved, it's been moved. It's not sitting where it originally was. It was originally a few miles further east, and then something gave it a big push and pushed a huge slab of rock westward over the underlying existing bedrock. So this whole region underlying the Taconic Mountains is rock that's out of place. It's not where it started. And the process of pushing that rock put it under tremendous pressure and turned it into metamorphic rock. So what are we talking about in the Taconics? We're talking about rocks like slate, which is seen in the upper video, and phyllite, which is seen in the lower video. Slates and phyllites are lightly to moderately metamorphosed versions of shales, of mud rocks. We also find some schist in the Taconic Mountains, which is a little bit higher grade metamorphic rock, but mostly we see what appear to be metamorphic versions of, say, the Normanskill Formation, which we see further west. And that's going to be a theme as we head down the east side of the Hudson. The rocks are going to have, in many places, the imprint of metamorphism, which kind of makes sense because plate tectonic collisions happen along the margin of a continent, and as you head east, you're getting closer and closer to the margin of North America, closer and closer to where these tectonic collisions were happening, so it should make sense that the rock shows more and more evidence of those tectonic collisions. Okay, so from the Taconic Mountains, we are going to head down to Poughkeepsie. And we're going to take a look at the rock that's exposed right along the edge of the Hudson River. This rock is very similar to what you find across the Hudson River to the west, very similar to the Normanskill. So let's go. And before we talk about the rocks in Poughkeepsie, there is one side trip to make, and that's to the town of Hyde Park. And Hyde Park is just north of Poughkeepsie. And what's interesting in Hyde Park is that there is a pond in Hyde Park. It's on a piece of property owned by the Lozier family, and there's a big pond on their property in their front yard. And they decided to have some people come in and drain the pond and dredge it out to make it deeper so they could use it as a swimming hole. And when they drained the pond, they found an entire skeleton of an American mastodon lying at the bottom of their pond. And being really good people, they probably could have sold the skeleton for a tremendous amount of money. Instead, they donated it to the Museum of the Earth, and paleontologists from the Museum of the Earth in Ithaca, New York, came and excavated the mastodon and cleaned it and reassembled it, and it is now on display in the Museum of the Earth in Ithaca. And if you ever get to Ithaca, New York, you have to pay the Museum of the Earth a visit and check out the Hyde Park mastodon. It is the most complete mastodon ever discovered. It has every single bone except for, I think, 2 toe bones. So it's an absolutely magnificent fossil of a large furry elephant that was roaming the Hudson Valley, probably about 10,000 years ago or so. All right, back to Poughkeepsie. Along the shoreline of the Hudson River in Poughkeepsie, we see some sedimentary rock from the Snake Hill Formation. And as I said, this is very similar to the Normanskill Formation, except that it's got a lot more greywacke in it, alternating layers of greywacke and shale. So the greywacke is the lighter, more sandy-looking material in the specimen, and the shale is the darker, muddier material. And in the Snake Hill Formation, you see alternating layers of greywacke shale, greywacke shale, greywacke shale, which show us that the greywacke was sand and mud that was being washed into deeper water periodically by storms and settling out into the mud that was already accumulating in the deeper water. And you can even see in the specimen here where the heavier sand was sinking down and mixing, starting to mix with the mud that it was settling out on top of. And then like the Normanskill Formation, the Snake Hill Formation, where you find it, you don't find flatline layers of it so much. You find evidence that after it was deposited, it was uplifted and tilted and folded. Not quite turned into metamorphic rock, but still given a good shove shortly after it was deposited. All right, from Poughkeepsie, we go to a little town called Poquog, not too far away, but further east. And actually, our next 2 stops are going to be in the vicinity of Poughkeepsie, where our last 2 stops, I should say. We're going to visit Poquog, and then we're going to head over to Wappingers Falls. Now, Poquog has a formation called the Poquog metasandstone. Right? What is that? What does that mean? Well, you have a rock that looks like a sandstone. It's got a lot of quartz in it, small grains, but it's also got minerals like pyrite and some mica that show you that this rock has been subjected to metamorphic conditions, metamorphic heat and pressure. So in many ways, the Poquog Formation is very similar to the Potsdam Formation. It looks like it at least started out as a very, very clean kind of quartz sand, probably deposited, as a shoreline, but it got caught up in some kind of plate tectonic event later on and turned into a metasandstone. And what's particularly interesting about the Poquog quartzite is it sits on top of the much, much older high-grade metamorphic rock that you see in the Hudson Highlands, that you see in parts of Manhattan and in the Bronx. So it sits on top of the basement metamorphic rock, and there's a nonconformity. There's an erosional surface and a gap in time of about 500 million years between the older high-grade metamorphic rock and this younger low-grade metamorphic rock. You see the same thing way up on the flank of the Adirondack Mountains, where you have the Potsdam sandstone sitting on top of metamorphic rock associated with the Adirondack Mountains. This what we call Grenville age rock, with about 500 million years of time missing between the two. So it's remarkably similar. You're seeing essentially the same transition from an ancient eroded surface representing the eroded roots of a mountain range to a shoreline sand deposit representing an initial sea level rise back in the Cambrian period. The main difference is that when you get down into southeastern New York, the overlying sand is not a sandstone anymore. It's a quartzite. It's been turned into metamorphic rock. And then finally, in Wappingers Falls, we see lots and lots of limestone. Similar in some ways to the limestone that you see up at Saratoga Springs or kind of surrounding the Adirondack Mountains. The Tug Hill Plateau region on the southwest of the Adirondack Mountains has broad regions of limestone from the late Cambrian and early Ordovician. So you're seeing essentially the same limestone in southeastern New York that you see up in central and western New York, except that in the southeast it's been turned into metamorphic rock, or at least it's on its way to becoming metamorphic rock. It's very crystalline looking. You know it's carbonate rock because it reacts with acid. But the fossils and some of the the sedimentary detail in the original rock is missing. It's been kind of recrystallized away. So this rock has experienced some pressure. And again, it makes sense because it's getting towards the margin of the continent where plate tectonic collisions were happening throughout the Paleozoic. Okay, so that is our tour of the different rock formations in the eastern part of New York, and from the tour and the slides and the videos, you should have enough information to fill out your field notes in the lab, and then from that you should be able to construct a geologic cross section. And let's see, let me all right, well, so thank you. Just to reiterate, you are going to use the information in this presentation to fill out the field notes. So each of the slides has a number associated with it, or most of the slides showing specimens have a number associated with it. With the specimen, you want to make a note of the rock type and the age of the specimen or specimens that are shown. And then you're going to take this information and use it to fill in the ages and the rock types on this paint by number cross-section diagram. And from this diagram, we will then create our interpretation of the geologic history of New York State. Okay, thank you for listening.